Hello everyone and welcome to our next Physics 6 lab. This one is called Thermal Expansion. Hopefully you have your data page already downloaded so you can fill in the data as we go. The goal of today's lab is to actually measure the coefficient of thermal expansion of a brass tube and also an aluminum tube. The formula for expansion, thermal expansion of something, delta L equals initial L times alpha delta T. So we know that the amount something expands, its change in length, is proportional to its initial length. It's proportional to the change in temperature, and it also depends on the coefficient of thermal expansion for that particular material. The goal of the lab today is to measure the coefficient of expansion for a brass rod. That involves us measuring the change in temperature, which is easy to do with a thermometer, and also measuring the initial length, which we can do with a meter stick, but we also need to measure the change in length. Now, you know, if I heat this brass tube from 20 to 100 degrees Celsius, it will expand, but it expands only a very small amount. Alpha is a very small number, and it'll probably be less than 1 millimeter. So if I were just to measure the length of this with the meter stick at the beginning and the length of the meter stick after it's warmed up, it would be very difficult to see the change in length of less than 1 millimeter. So what we need is a sensitive measuring device, and I want to sort of explain to you how that works so you can see what's going on here. Basically, I have a little arrow here. The arrow is attached to an axle so that you can see it spins when I turn the axle, and that little arrow sits. Let me give you a closer up view of this. Yeah. Okay, so we have a little protractor here, angle measuring device. We have our arrow. The arrow is on this tiny little narrow axle, and we lay the axle onto these, there's some wheels here. We lay the arrow on these wheels so you can see that as I roll my finger over the axle, the little arrow responds very sensitively because the axle is narrow. So a slight motion of my finger results in a large motion of the little arrow. And you can see it's pointing to different angles in the protractor. So that sort of amplifies the tiny expansion of the rod so I can measure it. To try to make it a little bit more clear, suppose this little rod here is our arrow, and this tape is the axle. So what happens is we take the brass tube. The brass tube is going to expand. As it expands, it rolls over the axle and turns the pointer to different angles. So the formula that we're using looks something like this. The change in length is going to equal to the initial length. Actually, the change in length is going to be, well, look, suppose the change in length caused the pointer to rotate 360 degrees. If that were the case, what would the change in length be? If the change in length made the pointer go around 360 degrees, can you see that the change in length is rolling around the circumference? So that would be one complete circumference. So if it turned 360 degrees, then the change in length would be the circumference of the little axle, which would just be 2 pi r where r is the radius of the little axle. But that would be for 360 degrees. Suppose it didn't rotate all the way around, but only halfway, or only a fourth of the way, 90 degrees, or only 45 of the way. Then you can see that the change in length would be the circumference multiplied by the ratio of whatever angle change was over 360 degrees. Okay, so 2 pi r is the circumference. So if the change in angle was 360 degrees, then divided by 360 would just give us the circumference. So if the rod expanded one circumference, then it would be 360 degrees all the way around. If this change in angle is only 180 degrees, that would be half a circumference, or 180 over 360, which is a half of the circumference. So whatever ratio the angle is to 360, that's the ratio that the delta L is to the circumference. So your handout writes it like this. That the change in length is to the circumference as the angle changes to 360. You might have to think about that a little bit to fully grasp it, but I hope you take the time and trouble to do that. So the actual setup of this is a hollow tube, and we're going to run steam through this. First I'm going to set it up. Let's measure the length of it. The length of the rod is actually the part of the rod which is situated between where it's supported here and where it's touching the little axle over here. So let me give you a closer up view of that. So we've got the tube supported at one end with a rubber grommet, and at the other end we have it lying across the axle of the pointer, and you can see it's very sensitive to motion. So the first thing I'm going to do is measure the distance from where it's supported here to where it's touching the axle there. That's the part of the rod whose expansion we're actually measuring. So let me take that data point. I've actually marked with a marker the point of contact, making sure that I got this right. That little mark has come off, so I'm going to put it on again. So I'm just going to measure the distance from the rubber grommet to that mark that I just made. And I can see that it's, you can see the mark here, hopefully. It's about 103.6 centimeters. So on your data page, for the initial length of the rod, we're going to put 106.3 centimeters plus or minus 0.1 centimeters. Notice here that we also need to know the diameter of the pointer axle so that we can have the radius of the pointer axle according to our formula. The pointer axle is pretty small, so to measure this we're going to use a micrometer. And I'm just going to put the micrometer onto the pointer, onto the axle, like this. And And then we're going to read the micrometer. These are millimeters. You can see there's 2 millimeters, and these are hundredths of a millimeter. So we have 35, 38 hundredths. So 2 and 38 hundredths millimeters, which we can write right here. 2 and 38 hundredths of a millimeter. This will be plus or minus 0.05 millimeters. We're going to take a half of that to give the radius. That'll be 1.19 millimeters for the radius. We'll just keep the uncertainty to be the same, 0.05. So now we have the radius of that little axle, about 1.19 millimeters. The material of the rod, you can write on your data page, is brass. This will allow us to compare the coefficient of expansion for brass that we get experimentally with the one that's the known value. Okay, so now I'm going to lay the brass rod. We've measured its length. We've measured the radius of the pointer. So now I'm going to lay the brass rod on the pointer, exactly where we measured it to. Now notice that it's very sensitive to motion. So what we're going to do, I'm going to take this rubber tubing, put it on one. We're going to run steam through it. First we need to find an initial temperature, which is just room temperature. So using our thermometer, we're going to read the initial temperature of the room. I don't know how well you can see that in video, but it looks like about 22 degrees Celsius. So again, on your data page, for initial temperature, 22.0 degrees Celsius. The final temperature is going to be the temperature of the steam, which we're going to take to be the standard 100 degrees Celsius. Okay, so initial pointer angle. See, this is what's going to change when the rod expands. The initial pointer angle, I'm going to try very hard to set that to 0. It's so sensitive, it's shaking. Now the tricky thing here is I'm going to connect the rubber tubing to the steam outlet. And as the steam runs through the tube, it's going to expand. The tricky thing is, I would like you to be able to see that expansion. So as soon as I plug the hose into the boiler, there's steam coming out of the boiler here. I'm going to try to get the camera as quickly as possible onto the pointer so you can actually see it expand. It goes pretty fast. I don't know if I can do it that quickly, but let's give it a try. Okay, I'm going to plug the hose into the boiler and bring the camera over to the pointer. I don't see the steam coming out. There should be steam coming out. Oh, look at that. Can you see it? You see the pointer is changing. It's going from 0. It's very hard to see because it's black, unfortunately. But you can see the angle of the pointer has changed right in front of your eyes. So you can see that the brass rod is expanding. We just have to watch it until it stops expanding. It's still moving. I think that's as far as it's going to go. So it went from 0 to, looks like 52 degrees of angle. So it went from the 0 here to 52 here, which means that the rod has expanded that much. Okay, so, all right, so the initial pointer angle, I tried very hard to make it 0 degrees. The final one we said was 52 degrees. So the pointer moved from 0 to 52 degrees. So that's the delta theta, theta 2 minus theta 1 that we're going to use in our calculation. Okay, now we're going to do it again for aluminum. So first thing I need to do is disconnect the steam. Try to remove the rod carefully because it's going to be hot, steam temperature. I'm going to take the brass rod and put it aside. And then we'll take the aluminum rod. We're going to measure its length between the contact points. I'll just do it for you. You have to trust me on this. Going from 0 to 79.7. So for the aluminum, we're just going to do one trial because of time constraints. So this is rod 1. We did trial 1. We're not going to do trial 2. For rod 2, we're going to use aluminum. Initial length, what did I say? I forgot. Looks like it moved a little bit. It's going to be 82. 80.2 centimeters, plus or minus 0.05 centimeters. Initial temperature, we'll take it to be the same as it was before since the room hasn't heated up very much, 22 degrees Celsius. Final temperature is temperature of steam, 100 degrees Celsius. And once again, I'm going to try to set the pointer at 0. Just check and make sure it's working. It's very sensitive to the position. Yes, I'm going to set it at 0. What do you think? Will the aluminum expand more or less than the brass? Well, first I have to hook the steam hose up to one end. Now everything just fell apart. Try to put it back just the way it was. Okay, let me check and make sure it's still working. Yep. Put it at the 0. Make sure we've got steam coming out. Yep, I feel it. So once again, I'm going to hook the hose up to the steam and then try to get you over fast enough to see the pointer move when the steam goes through. Are you ready? Here it goes. I'm hooking up the hose to the steam. Careful not to get burnt. Now let's take a look at the pointer and see if it's moved. It's already moved. Oh, look at that. Look at that. Look at it move. Wow. The aluminum is really expanding. Looks like it's expanding more than the brass. And in fact, the coefficient of expansion for aluminum is greater than brass. And it went to, looks like about 65 degrees of angle. So we can immediately write that into our data page. Initial pointer angle was 0, and it went up to 62 degrees of angle. Last time for the brass, it was 52 degrees. Okay, so success. We've got our data. Using this data, you can calculate the coefficient of expansion. This will give us our delta L. Solve for delta L, and then delta L. You get a better marker. Delta L equals L alpha delta T, so you can solve for your alpha. Delta L that we get from this formula over initial L and our delta T, which is just going to be 100 minus 22, 78 degrees. Then you can compare your experimental coefficient of expansion with the given values, and I'll make sure that you have access to those when you do your report. In your report, by the way, there's room for a third rod. We're not going to do that. We're just doing the 2 rods, 1 trial for each one. And in your lab report, you want to talk about the purpose of the lab. Talk a little bit about your understanding of how this measuring device works and the purpose of each part. The purpose of the little rod and the arrow was, of course, to increase the sensitivity for measuring delta L. Talk about which coefficient of expansion was greater. Was it for the aluminum or the brass? Talk about your percent errors, evaluate them, were they acceptable or not? And then, of course, as always, a comprehensive list of sources of measurement error. That's it for thermal expansion. Let me know if you have any questions, and good luck writing your report.